So today we're going to be looking at how we use rocks to tell Earth's history. We're going to be using the geologic, right, rock logic. And we're going to be looking at and applying the concept of geologic principles and looking at rock strata. So we can look at the geologic, kind of the concept of uniformitarianism. That geologic processes that we observe occurring today are assumed to be the same processes that have occurred throughout Earth's history. The quote by James Hutton, right, the father of geology, who I reference as Papa Geo, "The present is the key to the past," relates to what we see in today's rock record to past events that humans were not present to observe directly. So here's kind of a caricature that I think that explains that well. That we have this volcano taking place and we have a dinosaur, say, during the Jurassic. Well, volcanoes that erupted now during this, erupted during the time of the dinosaurs, right? There was volcanism then, there's volcanism now. But today, that old eruption is an igneous rock. So this sample right here is now rock here, and then we could say that, well, if the dinosaur made it into the fossil record, it would be another within the rock strata. So we can find the rock and determine what took place. We can find igneous rock and say, well, it must have erupted from a volcano. And if we find sedimentary rock that's got fossils in it, we could say, well, the conditions allowed for sedimentary rocks to form. So now let's look at sedimentary rocks and stratigraphy. So sedimentary processes are generally the breakdown and creation of new rocks. These are what we, as a part of the rock cycle, we call these detrital. A few simple and more important ideas that we're going to use logical steps that are driving the concepts that we're going to learn. So we just need a little practice. So let's look at relative age dating. It's simply the relative age of a rock sequence, or the layer of the rock strata, based on another layer. That this dating technique uses language such as older than and younger than. So if I look at this sequence of rock strata, the picture is saying that, so the deeper we dig, the farther back in time we see. It's just saying that the rocks on top, the upper layers of rock strata, are younger than the rocks below it. Where we could also say the rocks deepest in the right beneath are going to be older than the rocks above it. So we're using language such as older than and younger than. So younger rocks are above older rocks, or older rocks are beneath younger rocks. Whereas radiometric dating, we learned, provides an absolute age, as one can determine the amount of parent and daughter isotope and calculate the age of the rock, right? We know the half-life of, or the decay rate of certain minerals, and those minerals are found within certain rocks. So let's look at this as I drew a couple pictures here. So here's a geologic principle, original horizontality. The principle of original horizontality is that sedimentary layers are laid down horizontally, that it's only gravity settling down these particles. So I might have a sandstone forming here, I might have a conglomerate forming here, or formed here. These are rock layers. These are my strata. And I might have, say, a shale or something. So I have these layers, these really nice horizontal layers, that it's gravity equally distributing them. And then we apply the concept of superposition, that the younger rocks are on top and older rocks are on bottom. That the younger are on top of the older, or another way of saying it, older beneath younger. So we're looking at this sequence that we can say something using the logic, rock logic, geologic. Well, there's two more topics that I want to make sure we understand: cross-cutting relationships and inclusions. So I'm gonna jump to the inclusions. That if I look at a conglomerate, or a breccia, these contain rocks that are older than the new rock of the conglomerate. That this layer of rock has little fragments of rounded rock in this conglomerate here. That the fragments existed prior to the new conglomerate forming. It's simply the principle of inclusion. If it includes other rock, those rocks had to have existed prior to the new rock forming. And then I have what's called cross-cutting relationships, and this is a new one. That here I put in a fault and an intrusion, an igneous intrusion. Just because at depth we get igneous activity. It doesn't mean it was a volcano, it doesn't mean it reached the surface. It's simply called an igneous intrusion. It intruded these sedimentary rocks. That the fault and the intrusion are younger than the pre-existing rock layers in which they disturbed. That these rock layers had to have existed prior. If this fault occurs and all of these moved, right, or were redistributed, this might have been uplift or this might have been down, what's called subsidence, or falls downward. It does that along a plane that we call a fault. That if the fault cut through these layers, the layers existed, right? The strata existed prior to the faulting. And if this igneous rock cut through these layers, the igneous rock is younger than the rock layers themselves. So those are the geologic principles we're looking at. So if I start putting these all together, that we're going to apply the concept of stratigraphy and geologic principles. We consider them simultaneously. That the picture here, and I'll talk you through this here in just a moment, it illustrates the geologic principles. Uniformitarianism, original horizontality, superposition, inclusion, and cross-cutting relationships. And this is a picture I drew on our classroom whiteboard. That we're using rock logic, geologic. And we're going to use this to be able to determine what took place in the environment at which it took place, along with when it took place. So we discussed the geologic principles that help geologists determine the age of rocks, therefore telling the Earth's story. So let's look at this picture. So I have gravity depositing youngest material on top. And I draw this little key here. I just kind of drew sandstone with the dots. So sandstone are my uppermost, my youngest layer. I then have a layer of shale situated between the sandstone. So I've got sandstone, I've got shale, and I've got limestone beneath that even. And then beneath that limestone, I even have yet another layer of sandstone. So I get these rock strata that the youngest are on top, the oldest are on bottom. And I draw these. We'll start making pictures with a key so we can determine them. Remember, shale can contain fossils, and limestone can contain fossils. Shale creates an anoxic environment that preserves slows the breakdown or the decomposition of organisms, whereas limestone, when we find limestone, we generally find the hard shells of marine organisms. And in shale, we can find a broad range we can even find terrestrial organisms, right? Land-based animals. So we're going to be looking at relative age dating, right? Older than, older on bottom, younger on top. In radiometric dating, now we can apply and start putting a timeline to it, right? There's just so much that has happened in Earth's history that tells the story by the rocks that still exist. However, much of Earth's history has been erased by erosion. So just because it formed a rock at some point, that rock could have been broken down and weathered and eroded and can be completely erased from Earth's history. So we've got a lot of moving parts here. So the Earth's rock layers are like a book, that each layer is a different chapter. So this is what I want to have you make sure you take notes on, is what we're going to call igneous markers. And this is where we say that igneous rock, remember, once igneous rock crystallizes and solidifies, its radiometric clock starts. It begins. So as soon as rock forms, right, igneous rock, where we find volcanism, we get what we call igneous markers. So radiometric dating is the primary way in which geologists show what happened, whether it's an event that occurred on Earth or the evolution of kind of the changing of organisms, and precisely when it happened. We now can put a timeline to it. This provides the timeline of events of Earth's history. So in the picture to the left, you can see how to apply both relative age dating and radiometric dating and how they are used to determine when sequences occurred. And this is significant when understanding Earth's past. We have precise dates to put with different events. So if I look at this, both radiometric, relative age, and radiometric tell the age of organisms, when they lived, when they died. Essentially, this is supporting evidence of evolution, of a very grandiose idea of how and why complex organisms exist and where we came from. So let's look at the rock strata for a second. If I have this rock here, and this volcano might have erupted fairly recently, I get this rock layer kind of on the Earth's surface, right? We'll just call that today. But if I can go back and keep digging into this rock, and I find a layer of rock, and I might find fossils in here, and I find these fossils, but I also find this past volcanic material, I can radiometrically date that volcanic material and find a precise timeline. That if I use relative age dating, I simply know that this layer is older than this layer. But if I use radiometric dating, I can radiometrically date this, and I think my number got cut off here, but it's 1 billion years ago. I can radiometrically date that and say, these fossils occurred, I see these fossils about 1 billion years ago. And then in this other layer, it's a different type of rock. I find that this might be 1.5 billion years. I have a different type of rock, but now I have a timeline that I know that that this sample right here formed sometime in between 1.5 and 1 billion years ago. I'm now getting what we call igneous markers. The igneous rock I put a precise timeline to. So, and then this sample right here, and I don't know why I'm using billion years, because if I draw fish were definitely not available, were not alive 2 billion years ago, but I'm trying to drive the concept home. That there might have been another volcanic eruption, right? A volcano doesn't just erupt once. They have these infrequent and sometimes these periodicities in which they recur. And in this case, I might have another igneous marker down here. So I can put together a timeline in which events took place based on the igneous rock that's kind of laid down kind of in and around the sedimentary rock. So we call these igneous markers. That when I couple the idea of using both radiometric and relative age dating, I can actually speak very, very intelligently about the sequences that occurred, when they occurred, and what was happening within that environment in which was forming the rock. And it puts together just a really unique and cool storyline about talking about what was taking place on Earth without actually having to be there to witness it directly.